No questions before we begin? All right, not hearing anything. So we're going to be doing, I thought I had that up there. We're going to be doing lab 6 today, disc diffusion and antibiotics. Anything else I need to talk about? You should be, no. I'm going to be sending out the unknown project, the instructions and the first data and your number on Tuesday. But you should be working on your infectious disease paper. It is due Saturday, November 11th. And I know a number of you have requested a topic. There's a few people who requested a topic yesterday. I haven't replied to my email, so I'll be getting to you after the lab. Any question about any of that? All right, if not, let's go ahead and I think I can close that. Go to lab 6. 6, disc diffusion, evaluation of disinfectants and antiseptics, and antibiotic effectiveness. There is some reading to do, as in all labs, so I'll make sure you get that done when you're doing the lab. There are some supplemental materials, some video clips, and we do have a virtual lab today. Any questions about any of that? All right. So yeah, we'll have a virtual lab today, and it's actually kind of fun. Virtual lab is good because you get to do what students who are going into the lab, you actually get to do what they're doing. It's just you're doing it on the computer. The learning objectives for today's lab: identify the type of chemical agent and active ingredient used in various disinfectants and antiseptics. 2, evaluate the effectiveness of disinfectants or antiseptics using disc diffusion. By the disc diffusion, we mean the Kirby-Bauer test, and I'll talk a little bit more about that. 3, determine the mode of action of various antibiotics. 4, evaluate the effectiveness of various antibiotics using disc diffusion, meaning the Kirby-Bauer test. 5, list variables that influence the antibiotic disc diffusion susceptibility testing. And 6, define the terms sterilization, disinfection, disinfectant, antiseptic, a bactericidal agent, a bacteriostatic agent, and an antibiotic, the spread plate technique, and a zone of inhibition. Any questions about what we're covering today? All right, let's move on as soon as I can get that going. So the introduction: sterilization refers to the elimination of all viable organisms, including endospores. We're only talking about something that's cellular at this point. When you sterilize something, you may not remove a prion, but other than that, sterilization removes all viable organisms. Disinfection refers to the destruction of vegetative cells, not necessarily endospores. A disinfectant is a chemical agent applied to an inanimate object. Like when we use bleach to clean the toilet, bleach is a disinfectant. Any question about any of that? That differs when we use the chemical on living tissue. That we call an antiseptic, a chemical agent applied to living tissue. Now, if you use bleach on the toilet, but then your cat comes back all bloody and you use bleach to clean the wound, bleach, the same chemical, is used in one case as a disinfectant and in the other case as an antiseptic. And yes, I'm aware that most people do not use bleach on their cats because bleach is pretty hard on living tissue, But it used to be, and it still could be, I don't know, when they first ran into necrotizing fasciitis and they were wondering how to treat it, they found that, yeah, you give the patient antibiotics to stop the necrotizing fasciitis, but you wanted to take the wound and wrap it in, not Band-Aid, but a wrap, whatever you call those things, in bleach, and then apply the bleach. So that was a treatment for necrotizing fasciitis, at least in the past. It's possible that now they have another treatment which works as well at killing the necrotizing fasciitis in the skin, but it's not as harmful to the tissue. So it's possible they have another treatment now. But in the past, that was one treatment they definitely used, bleach. And it would be used as an antiseptic in that case. To evaluate the effectiveness of chemical agents, you can take a nutrient agar plate and inoculate it with a particular particular bacteria. And then have the bacteria sit a while before you add a disc saturated with a different chemical agent. The chemical agent will then diffuse out of the disc and into the agar, establishing a concentration gradient in the agar around the disc. You then allow the plate to incubate overnight for the bacteria to grow and look at the bacterial growth pattern. If you find a zone of inhibition around the disc, an area with no bacterial growth, you can assume the chemical is at least a little bit effective on that particular bacterium. Conversely, if there's no zone of inhibition, the chemical can be assumed to be ineffective, at least on that particular bacteria. That is not saying that the bacteria is sensitive or resistant to that chemical. We're just saying that the chemical is, at least to some degree, effective or not effective against the bacterium. Any question about any of that? All right, table 6.1 shows you some common disinfectants, their preferred use, and then the chemical agent as well as their category, like ethanol and isopropanol or alcohols. They are typically really a degerming agent, and that's because they're very weakly an antiseptic. We don't even call them a disinfectant because they're very weak disinfectants. But they do degerm the skin. They do not remove all microbes from the skin. They just reduce their number to safe levels so that then you could give a needle injection in the area, for example. Aldehydes, including formaldehyde, formalin, glutaraldehyde, are all disinfectants. This is one type of disinfectant that actually kills endospores. Another type of disinfectant which kills endospores are peroxygens, like hydrogen peroxide. Hydrogen peroxide is probably in most homes, and it's used as an antiseptic, and it is one that actually kills endospores. So that is a common one that we use to kill endospores. Formalin and formaldehyde, I don't think most people have those in their homes. Halogens include iodine and chlorine, like chlorine bleach. Iodine is used as an antiseptic, the chlorine bleach as a disinfectant. And that's because iodine is not very harmful to the skin. It's a good antiseptic. In fact, in hospitals before surgery, they used to always use iodine. Nowadays, they have better agents, and so they're not using iodine. I don't think anyone uses iodine anymore, but it's certainly not often used before surgery. But before, it used to always be used before surgery. Heavy metals are a disinfectant, sometimes used as an antiseptic. For a while their use was discontinued, but because of the resistance of microbes to other disinfectants and antiseptics, as well as antibiotics, the use of heavy metals has come back. For example, they will often put heavy metals in the Band-Aid or a gauze to prevent the tissue from becoming infected when you have a wound. Peroxygens I've already talked about. Hydrogen peroxide used as an antiseptic, and it's actually a very good endospore killing agent. Phenolics, compounds with phenol or like phenol, usually used as an antiseptic in low concentration. The problem is phenolics are actually pretty irritating to the skin, and they have an unpleasant smell as well. They more often are used as a disinfectant to clean an area. And then surface active agents, these are the new things that quaternary ammonium compounds that hospitals use. They're a very good disinfectant, and they can be used to clean what do you call it, surgical agents or things like that you wouldn't want to put in an autoclave. All right, any question about any of that? The zone of inhibition size depends only partially upon the bacteria's sensitivity to the disinfectant or antiseptic or the antibiotic. There are various other factors that affect the size of the zone of inhibition, including the concentration of the chemical. Generally, the more concentrated the chemical, the larger the zone of inhibition. The molecular weight of the agent will affect the size of the zone of inhibition. The smaller the molecular weight of the chemical, the larger the zone of inhibition. And the density of the bacterial inoculum. Generally, the heavier the density, the smaller the size of the zone of inhibition. Any question about any of that? So the size of the zone of inhibition is dependent upon a number of factors, including how sensitive the bacteria is to that chemical agent. When we're evaluating antibiotic effectiveness, it's important to categorize an antibiotic as to whether it is bactericidal, that means it kills the bacteria, or if it is bacteriostatic, if it inhibits the growth of the bacteria. If you treat with a bacteriostatic antibiotic, the bacteria cannot grow, and that will allow time for the immune system to eliminate the infection. But the chemical agent or the antibiotic itself will not remove the bacteria. It just prevents the bacteria from growing. Any question about any of that? I guess the bad news is if you were to give an antibiotic that was bacteriostatic and the patient had a poor immune system or no immune system, once the antibiotic would be stopped being given, the bacterial infection would come back and would grow again, causing the infection again. Any question about any of that? The Kirby-Bauer disc diffusion test is the most common method for testing antibiotic sensitivity or resistance. The results of such testing help physicians in choosing which antibiotics to use when treating a particular patient with a particular bacterial infection. Bacteria can be isolated from the patient, grown on an agar plate. An impregnated disc containing different antibiotics can be added, and then you can incubate the plate and then look for the zones of inhibition and determine which antibiotic would be the best one to treat the patient's infection. Now, the zone of inhibition does not necessarily mean that the greater the zone of inhibition does not necessarily mean that the antibiotic is more effective. Let me blow this up. That should be good enough. So from here, we see this one has the greatest size of the zone of inhibition. Let me blow it up a little more. But is it the best antibiotic? It could be it's the smallest antibiotic, so it diffuses further than, let's say, that antibiotic or that antibiotic, which are much larger. So to determine the sensitivity of the bacteria to the antibiotic, you have to consider the diffusion rate of the antibiotic, the degree of sensitivity of the microorganism, and the growth rate of the bacteria. Table 6.2 lists all of the factors that we control when doing the Kirby-Bauer test to make the results similar from one test done by one person in one part of the world, so that they will get similar results to another person in another part of the world doing the same Kirby-Bauer test, meaning you're using the same bacteria and using the same antibiotics. First, you inoculate the nutrient broth using several colonies isolated on non-selective media. The cultures are not grown more than 24 hours old. You then grow it in a broth and adjust the broth turbidity to 0.5 Macfarlane units. That's approximately 1 times 10 to the 5th microorganisms per mil. And then use that. If you, like I said, you use higher density bacteria, you will get a smaller zone of inhibition. And then you inoculate at room temperature, always a Mueller-Hinton agar plate. Different media can affect the size of the zone of inhibition. We also have the pH of the Mueller-Hinton plates between pH 7.2 and 7.4. So the pH doesn't affect the zone of inhibition. And you have the agar at 4 millimeters thick, because the thicker the agar, the slower and the less the antibiotic will diffuse. The thinner the agar, the further it will diffuse. So the thickness of the agar will determine the size of the zone of inhibition. And then we have a plate of 150 millimeters in diameter, and we take the bacteria and swab it onto that plate with a non-toxic swab to obtain confluent growth, so the bacteria will be growing everywhere. You then put the disc on at least 24 millimeters apart. Let me go back to here. Put the discs on so they're at least 24 millimeters apart. No more than 12 discs on the plate. And you put the antibiotic disc 5 minutes after you put the bacteria on, and not longer than 15 minutes after putting the bacteria on. Once you put the bacteria on, you let it sit for a few minutes to absorb the liquid that the bacteria were on. And so you always let it sit for 5 minutes to 15 minutes before putting the antibiotic disc on. You then place it in the incubator no longer than 15 minutes after placing the antibiotic disc on the plate. And it should be an incubator that doesn't have CO2 added to it. And then you incubate for 16 to 18 hours at 35 degrees C. Obviously, if you use a different temperature or you incubate it at a different time, you can have a different size of the zone of inhibition. You then incubate the plates and then look at the inhibition zone sizes. Simply looking at the zone and seeing that that's greater than that one doesn't mean that's the best antibiotic to use, because this could be a much smaller antibiotic, in which case it will diffuse further and create a larger zone of inhibition than an antibiotic which has a larger molecular weight size. So what you need to do is measure the diameter of the zone of inhibition, and you just take the ruler over it and then measure over the center of the disc, get the diameter, and you usually do 2, and then take the average diameter, and then compare this zone of inhibition to a table set up by NCCLS, the National Committee for Clinical Laboratory Studies. That's what NCCLS stands for. They have the table showing you the size of the zone of inhibition for each antibiotic, for each bacterial strain. And if, for example, Staphylococcus aureus was the antibiotic, was the bacteria we're testing, and penicillin G was the antibiotic we're testing, if the size of the zone of inhibition is 20 millimeters or less, we say that this bacteria is resistant to this antibiotic, meaning penicillin G. If, on the other hand, the size of the zone of inhibition is greater than or equal to 29 millimeters, we then say that this bacteria is sensitive to this antibiotic. And between these two, from size 21 to 28, we say that the bacteria is intermediate to this antibiotic. Each species of bacteria will have a different size of zone of inhibition for each antibiotic. Any question about any of that? So what we have for Staphylococcus aureus could differ for what the resistance is for the zone of inhibition for Staphylococcus epidermidis, and certainly would be different for E. coli, because that bacteria is very different from Staphylococcus aureus. Any question about any of that? So you have to measure the diameter of the zone of inhibition in millimeters and then compare it to the table of the NCCLS standards to determine if the bacteria is resistant to this antibiotic or sensitive to that antibiotic. And that's how we determine if the bacteria is resistant or sensitive. You simply just can't go and say that's the largest size of the zone of inhibition, so I want to use that one. Because if that's a small molecular weight antibiotic, we expect the zone of inhibition to be bigger. Any questions on that? All right, know the terms of this lesson. You're not going to be physically performing any of these activities, but you will be held responsible for how to interpret the effectiveness of antibiotics using the Kirby-Bauer disc diffusion test. In procedure 1, we're going to be preparing a spread plate. So view the video clip on preparing a spread plate, and then review the steps using aseptic technique for preparing a spread plate or a bacterial lawn of growth. And let me just go ahead and demonstrate that. What you want to do is take a sterile cotton swab. We're going to pretend that this is my stock culture. Take the cotton swab. Hopefully you guys can see this. Stick it in the stock culture. Obviously you want to shake it before you open it. And take the side of the cotton swab and touch it to the side of the glass to get the worst of the liquid off the cotton swab. Then take the plate and let me take these out of here. You want to do it like this, but I'm not going to show it like this, but you then swab everywhere on the plate. And that's a little too hard to do, so I'm going to actually do it like this. Swab everywhere on the plate. The plate will be round, so it'll be a little more difficult than this is showing you. And then what you do is you take the swab and you rotate it a quarter of a turn. You take the plate and you rotate it a quarter of a turn. Once again, you swab everywhere on the plate. The idea is to get the bacteria growing everywhere on the plate. Then you take the swab, rotate it a quarter of a turn, rotate the plate a quarter of a turn. And then you do this for at least 3 times, occasionally 4 times, and swab everywhere. It depends on the directions you're following. Some authors say 3 times, other authors say 4 times. We're going to pretend that we're done here, whether it's 3 or 4 times. And you should get bacteria growing everywhere on the plate. You then take the swab and you take it around the edge of the plate, which would be round, but this isn't quite round. The reason why you do that is to get the bacteria to be growing on the edge as well. Because when you're streaking on a plate, it's quite frequent that you may not get way to the edge. You then let the plate sit for about 5 minutes to absorb the liquid. And then you put the paper disc on the plate. Place the cotton swab in a container of biocide. Put the paper disc containing the antibiotics on the plate. Let it sit for just a few minutes, no longer than 15 minutes. And then write on the bottom of the plate what it is, what the test is, what your name is, what the date is, what the media is. And then sit the plate upside down in the incubator overnight. Any question about any of that? The reason for doing the swab everywhere on the plate and doing it 3 times is you want the bacteria to grow everywhere on the plate. We call that a lawn of the bacteria. I once had a student who, I don't know what she was thinking. She said, oh, let's go da 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 da. And so she had her plate with huge areas where there was no bacteria. She then came to me and said, I can't measure my zone of inhibition because the disc is right here and there's a whole region with no bacteria. And I said, well, you didn't get the bacteria to grow on a lawn. You were supposed to swab the plate everywhere. And I told her you can't use that plate. You're going to have to do the experiment again. So make sure you do swab it everywhere. Obviously, this is an online class. So in your case, it'll just be pretend. And we'll show you a video clip for doing that. So watch the video clip on preparing a culture for Kirby-Bauer disc diffusion. And then watch a little video on the interpretation of the results of the Kirby-Bauer disc diffusion. And then go to the virtual lab. Let's see if this works. I might have to use a new link. What the heck is that? Oh, I don't know. Start the thing. And then you can take this ruler down here and actually measure the diameter. Go across the center of the disc. You will only be able to do it one time because you can't take the ruler and do it here, but you could move it up there. That looks like it's about 30. And that looks like it's about 32, 30 millimeters. And that's C. C is for chloramphenicol. And then select what it is. This is, let me see if I can blow that up. This is the resistant column. That's the intermediate column. That's the susceptible column. So C, chloramphenicol with 30 millimeters. So that's sensitive. And if it's green, you made the correct selection. For CF, we'll do that one here. And it looks like that's about 17 for CF. I'm going to take the wrong one. So it's actually here. I'm going to take green, 18. Oops. Let me redo that one. Ah, now that I've done that, I see it is 18. All right, let's go and take another one. TE. Make sure I'm close on that. Once again, 17. TE. So that should be intermediate. Let's go ahead and take that one. If it's wrong, it'll give you an X. So that one's an intermediate because, like I said, I thought it was 17. So if it's correct, it'll be green. If it's wrong, you'll see an X. Any question there? So do that again on all of these and then restart. It'll come to another plate. This one, we have a different bacteria, Pseudomonas aeruginosa, and you can see that for C, it's going to be different. Something like there. So about 19 chloramphenicol. Once again, that's going to be. Oh, I wasn't reading that. That's actually 14. 19 is way up here. So 14 for C is there. And then you can do it again. We have a third. You have to restart each time to get it, a different one. We have a third bacteria. And there we don't have many which have a zone of inhibition. In fact, I only see one. And that's vancomycin. About right there. Maybe 16, maybe 17 for vancomycin. Is that VA? Yes. So that should be sensitive. All right, any question? For S, what you do is you just measure the zone of inhibition, and there isn't one, so you just measure the disc, and you don't need to do that, but that would be about 6, and that's S for streptomycin, so it's resistant. That's green, that's right. And all the others should be resistant, because I'm not seeing anything except for vancomycin that has a zone of inhibition here. All right, any question on that? If not, let's close that down. I have no idea why that's there. Just close that whole browser down. All right, so 2, using the standards required for the Kirby-Bauer disc susceptibility test, an E. coli culture is prepared using the spread plate technique, meaning the Kirby-Bauer technician, Kirby-Bauer test. Antibiotic discs are placed on the surface of the agar and incubated overnight at 35 degrees. Below are the results with the NCCLS zone standards used for interpretation. And I think this is in the worksheet, so let me go to that. So what you do is you measure the zone of inhibition and then look at the NCCLS recommended zone standards. We're only using E. coli, so you only need to do it for here. We don't have it for Staphylococcus aureus. And that's because I truncated the picture here. The picture would have gone off the screen if it had been both of them there. So there's the zone of inhibition. The dashed line, and the calipers are measuring it. To measure the caliper, you have to read from 0 to 0. You cannot read from here to there, because if you notice, right here is not where the 0 mark is. So you have to read from 0 to 0, and that is about 15 millimeters for ampicillin. I'm actually giving you the answer for ampicillin. So in the table here, put the size of the zone of inhibition, 15, and then get the interpretation. You find out where 15 millimeters is in this table, and then put your interpretation here. You only need to say S, I, or R, S being sensitive, I being intermediate, R being resistant. And then do that again for cephaloph. Sorry, I'm having trouble with that one. Cephalophen and gentamicin and tetracycline. And once again, we have the calipers having the measurement. Remember to measure that from 0 to 0. And so this 0 right there, you can see it there. And then 0 to 0, you can see it here. And then 0 to 0, you can see it there. So that's how you work the calipers. You do not measure them from here to here. And then see, that's something like, I don't know, 13, because that's not where the 0 is here. Any question about that? All right. Then list 5 variables that must be standardized when performing the antibiotic susceptibility test using the Kirby-Beyer diffusion method. And these were given to you in a table in the lab module. It might have been discussed in the text as well. Oops, it's not here. Where is that? Right there. So it was in the lab module. Find the table and then give me the at least 5 variables that must be standardized to perform the Kirby-Beyer test. Any question about that? 4, the size of the zone of inhibition often varies for 2 different species of bacteria when challenged with the same antibiotic. What is a possible explanation for these differences? Give your answer there. What would happen if we didn't use aseptic technique to put the antibiotic disc on the plate? And you should mention, I'm going to add this here and maybe upload it. What's going to happen to our test results? Okay. So, yeah, you're going to get probably contamination if you don't use aseptic technique. I want more than that. I want you to tell me what's going to happen to our test results. Okay. And 6, what would happen if we increased or decreased the concentration of the antibiotic in the disc? Be specific in your answer. So you must tell me what's going to happen to the size of the zone of inhibition if we increase the antibiotic in the disc, and what's going to happen to the size of the zone of inhibition if you decrease the concentration in the disc. If you only explain one, you're going to get this partly wrong. Antibiotics can be bactericidal, that is, they kill the microbe, or they can be bacteriostatic, that is, they inhibit microbial growth but do not kill the bacteria. When observing a zone of inhibition around a disc, how would you determine whether the antibiotic causing that zone was bactericidal and or bacteriostatic? This is a difficult question, and students often get it wrong. You have to think about this one. So it is a thinking question. Okay? Any question about that? Hopefully, most of you will get it right on the second grading, because most of you will get it wrong on the first grading. Any questions about that? All right. When performing antibiotic sensitivity testing, it's important that the test conditions are kept very standardized, meaning you have the same kind of media, the same agar depth, the same age of the culture. Why? Give your explanation here. 9. Are there other substances besides antibiotics that we could evaluate using this method? The method they're talking about is the Kirby-Bauer disc diffusion test. Any question about that? All right. 10. Does the presence of a zone of inhibition necessarily mean the bacteria being tested is, I'm going to say, sensitive to that antibiotic? Explain your answer. Okay. All right. And I will put those questions up. I should put another one up, but I didn't do it earlier, and I meant to do it earlier. So, all right, if there's no questions, I will be here until 8 o'clock or the last student logs out to answer any questions and help you with the lab. I will warn you once again that number 7 is very challenging, and you will have to think about that answer. Okay. It's just that most of the time students get this wrong the first time. And like I said, you just have to think about it. Once you think about it, I think you'll get the answer. All right. Any questions? If not,